Skeptic, Graphs and Networks, the podcast exploring how the graph data structure has an impact in science, industry, and elsewhere.
Dave touched a core issue about working with networks and graphs that has implications on the use of graph database, and that is data exploration. I guess most of us intuitively, we use a scenario-driven approach or an analytical approach towards our business. We know what we need, and now we're just trying to figure out how to get it. In this case, a GraphDB is just another tool in the long tail of tools. It can help, for sure, like in some cases make their runtime faster. But I think the real power behind networks and graphs is in the exploration.
Sure.
Graphs are a great tool for exploration and to find out what we don't know. For example, Dave talked about community detection in order to find interesting clusters that might be involved in fraud. Here, instead of trying to picture how a network of fraudsters looks like, we can just use the network laws like community detection to help us find the anomalies in the data and point us in an interesting direction. If you find something interesting by using exploration, you can maybe later put it into production, maybe with or without a GraphDB. But networks, I think their main power lies in exploration.
In that context, I feel like the graph database is critical because if I want to do work on just my machine, like in a typical case, like let's say user data on a website, I can do a random sampling of users and that population is representative. So I can take a slice of the data, even a small slice, do some statistics on it, no problem. But it's not clear how I can random sample the graph. I guess I would random sample the edges, but it'll look like this very sparse graph. A sampling doesn't tell much of the story of the graph, I think. I really need to query the full data set.
You can let the algorithms, the network algorithms, find the interesting parts in the network for you, meaning like doing community detection, then asking which is the most central community in my data set and asking why is it the central community in my data set. Then dive into the communities and look for the central nodes in each community and ask yourself, why are the central nodes? And these questions are the explorative questions, right?
So your notion of exploration begins with the standard set of algorithms. My instincts were I want to write ad hoc queries of the network. But you would first look for communities and centrality and these sorts of things. Is there a standard list, or do you have to bring the domain into consideration when you pick which algorithms?
What I mentioned is community detection and using centrality measures. I think it's the best practice. It might not be relevant to each data set, but I think it's a good practice to start with, especially with large or huge networks, right? And small networks, maybe we can skip community detection, but usually I'll start with that. And then you can dive into the places that the network algorithms tell you, here's something interesting, take a look.
Well, here's something interesting. Take a listen.
My name is Dave Bechberger. I am currently a graph architect at Amazon, or on the Amazon Neptune team at AWS, but have worked in the past at a variety of different companies working with graphs, both as a consultant, as a implementer, and now as second company that provides it out to end users. So happy to talk with you today about my own opinions on how all of these different things work.
You are also the author of Graph Databases in Action. To kick off, can you give us the high level on the book?
Yeah, so Graph Databases in Action is a Manning publication that I worked on. It came out a couple of years ago at this point. When I started the process of writing a book, it really was, I wrote the book for myself 5 years earlier when I was learning graphs. What it was that I wish that I had known when I started working with graphs, and how, using that to help make other people make the process easier for others.
And could you share some details on the role of a graph architect? What is your day-to-day like?
What I do is I work with customers, our engineering teams, and in customers' internal and external engineering teams and product management to really help people adopt graphs and be successful using them. Not only working directly with customers on their use cases to make sure that they're actually able to be successful with it, but also what taking learnings from those different use cases, bringing those back into our product, and making sure our product can be, making sure they get integrated in our product in a way to make it easier to use.
So for people who are at the starting line, What is step one or question one for exploring graph databases?
I think the first question is what problem, making sure you understand what problems you have and whether those problems are good fits for graphs. And then for graph databases, because those are kind of two separate things. There's a lot of, especially as, developers, we use graphs all the time, even though we may not realize it. Linked lists are a graph. But, understanding is the problem I'm looking at best solved by using this type of data and this type of data structure? And then what are the requirements around that? And that kind of leads you down the path of, is a graph database the right solution or is something else?
Do you find that people in general have good instincts, or is graph something you have to get the hang of?
The very beginning of getting started with graphs is something that us as as developers already are doing because we're using these sorts of data structures. I think the real challenge comes when you want to move beyond the little toy graphs into something that actually solves more business use cases, starts, problems that when you start to scale not only data size, but also queries, the number of queries, the complexity of queries, the types of queries. So I think that's usually where I see most people to try and start to trip up.
So most organizations run a relational database. You can correct me if I'm wrong. I would be very interested to talk to a company that only ran a graph database and not a relational one. But what is the motivation to make that leap? Why can't I just cram everything into my traditional relational database that everybody knows?
I mean, you can, and people do all the time. It really comes down to it's like any other, I always kind of look at graphs as really like similar to any other NoSQL technology. They're all purpose built to answer a single or set of questions, really, when it comes down to it. You use key value stores for very specific reasons. There's a reason Cassandra or DynamoDB are out there to solve very specific problems. You use Mongo to solve very specific problems. Graphs are useful for solving very specific types of problems. And really, it comes down to the problems where the data you need to be able to answer those questions requires that you have to look through a lot of different connections. The one I always kind of use is kind of the canonical, or I should say, one of the canonical use cases is something like a social network. If I have a relational database, it's very easy to find who are my friends or who are my friends of friends. But now try to extend that and say, how are Kyle and I connected on LinkedIn? That's a very difficult thing to be able to answer in a relational database because of the fact that the query languages and the data structures just aren't built to be able to efficiently handle those things. So, in a relational database, you probably have to do some sort of recursive DTE type query, which I don't want to think about, think back to when I had to write those sorts of queries. They're difficult to write, they're difficult to maintain, and they're really hard to make perform. They're just not, and those sorts of queries are the ones that just relational databases aren't built for, and graph databases are. So I see them as, graph database is a great way to augment the other pieces of data you have, or I should say the other data stores you have in your environment.
And there's lots of reasons to move to graph. The example you gave is like, what n order friendship connection do we have? Which, yeah, I don't even know how I'd approach that in SQL.
I've done it before. It's about like that much SQL in very small font, and it's like 2 lines in a graph.
Sure. Are there other common reasons, entry points? Like, maybe I know PageRank is a famous graph algorithm that some databases either have natively or at least can support your usage of. Are there algorithmic cases that draw people to graph databases?
Yeah, I mean, and I would even extend it beyond a little bit just around algorithms, but there's also analytical type of use cases. There's certain types of insight that you want to derive out of your data that is kind of uniquely able to be found by graphs. PageRank is a great example of something that's called a centrality algorithm, or determining how important something is inside of a network. When we actually look at data, data, when we think about it in the real world, it's all, in most cases, it's a network is actually the way you want to think about it, even if it's something like a bill of materials. A bill of materials is a network. It's things that are connected to other things. Those things have attributes associated with them. And being able to look at that as a graph and being able to use that to help derive insight into something like, what are the biggest risks in my supply chain? Well, if you have all of these different bills of materials, you can start to figure out which of the suppliers is not necessarily the most, if you wanted to figure out which one of these parts is the most connected, that's pretty easy even to do in a relational database. It's a simple aggregation. But being able to figure out which of these is kind of the hub or the central piece here, where if I don't have it, it's going to impact the most things, is something where you can start to use a graph for that sort of thing. And that can be either done through algorithms such as PageRank. Community detection is a very common one for community detection algorithms, I should say, is very common in things like fraud use cases because you want to find groups of people that are colluding together. So, there's sorts of at, unique things are in or that are just intrinsic to the data structures of graphs that allow you to kind of get out insights in ways that other data structures don't have you to do that. And then I'm saying data structures there specifically because you don't necessarily need a graph database to be able to answer those sorts of things. There's lots of libraries out there like, uh, Network X. If you want to do it, you can do this sort of thing. But doing that at scale is when it usually starts to be more challenging at scale within a certain amount of time.
So NetworkX is a great tool. I've used it for a lot of projects, but as you say, it's not going to scale past my one machine, at least not in a clean way. Is there a rule of thumb for when an organization's going to outgrow a tool like that?
I mean, usually where I start to see that, organizations wanting to switch towards a more graph database is one of two things. Either you're dealing with a scale of data, well, I should say, when I look at any sort of data project, there's kind of two phases. There's the exploratory phase of figuring out what exists in there, and then there's the productionization phase of now that I know what's there, how do I actually move this into, my actual data pipelines? Because you got to start with figuring out what's there, and that usually, you want to move towards, you may start with Network X, but you're only going to be looking at a small subset of your data. It's great to start. It's great to start to, you can start to feel and understand what your data looks like. Then you want to be able to scale that up to make sure that the patterns that you're looking at aren't just in that small subset of data, since you're just like a sample. And that usually kind of that scale up is when I start to see people wanting to look at different technologies to optimize those sorts of things on the exploratory side. And then when you start to take this and you want to go to production, you're probably, if you have data at any reasonable scale, you're going to probably want to look to something that's a little more optimized to be able to answer this thing than a Network X type of library. Network X is a great library, but it does have its limitations of being written in Python and memory and all of the things that you get with running things in Python.
Well, on the relational side, I've, on many occasions, especially bigger orgs, worked with a database administrator, someone whose sole job was, add the indices, debate the schema, do performance tuning, overall maintain the system. Is there an analog in graph databases?
I mean, there at some organizations, I have seen kind of a graph database administration sort of role where it's usually, usually it's a a relational database administrator that also does this sort of thing. But I think it's also a bit similar to most NoSQL technologies that I've had experience with, where a lot of times it's a blurred line. Because it's a bit of a non-traditional sort of role where a lot of times the development and operations team ends up doing a lot of those pieces of work around the management of that sort of system. So it's actually one of the challenges with getting adoption is exactly that problem. There aren't people with 30 years of experience running graph databases in production, whereas there's multiple people that have that amount of work with relational databases.
And in the relational world, it's not a true dichotomy, but I sometimes look at databases that are meant for real-time transactional work versus those that are like a data warehouse for analytical work. Do you see the same distinction in graphs?
I do see the same distinction in graphs. There's quite a few databases that are meant for either OLTP type transactional workloads or OLAP type of workloads. But I would also draw a little bit of a differentiator there in as much as there's sort of there's databases that are meant for those things. And then there are kind of other in-memory library or frameworks around those sorts of things where you have these sorts of graph processing frameworks up, graph frames for, Spark, if you want to do something like that. That's really solidly aimed at the OLAP sort of market. It runs on Spark. You're not running real-time workloads on Spark. You're running inside of that framework, and that framework is really, a graph framework, but not a database in the traditional sense, I would say, at least.
There's I don't know if a ton of choices, but certainly several choices one can make. There's a lot of vendors out there. What's the typical decision tree look at when people go and decide what to choose?
From a database perspective, I mean, I think it comes down to a couple of different things. There's, ease of use would be a very common one. Developer productivity, cost is another very common one. as well as management. Is it a managed? Is this something I have to manage myself, or is this a managed service, or does my preferred vendor even offer a managed service? And then there's those sorts of things too. I mean, as I said, I work at Amazon, and one of those things, one of the big selling points we have a lot of customers is it's a managed service. So for a lot of those operational headaches that I talked about a minute ago don't necessarily exist for that. Many of the other vendors out there also support similar things, but all of them are a little bit different. But those are usually where we see people kind of start with ease of use, operational headaches, and cost. I would say it's probably not much different than most than the decision tree for most relational databases. I guess the other part there is, what do other people in your company actually use? What do you have experience with internally?
And do you have a sense of the maybe industries that most often come to graph databases, or perhaps it's the departments like finance versus something else? Who is the really leader in bringing something like a graph database into an org?
I think that who really brings a graph database into the org probably depends a little bit on the industry that you're in. I mean, but a lot of times it's the R&D type departments in certain industries, as well as like the data engineering department. So especially if you're working, a very common industry that has been probably one of the early adopters of graphs and graph technology and graph databases is like the financial services industry, where they're looking for fraud. I mean, fraud is a kind of a very common graph use case. So being able to have, but that usually involves your R&D departments looking at what does fraud actually mean in your specific environment. Because, having worked with a lot of different fraud customers out there, there's general patterns of what fraud looks like, but what fraud actually looks like is very different every single, end user and every single department, or even different departments within the same organization. So you have a lot of like R&D data science people that are using that. When you start to think about some of those other use cases, security graphs being a very common one, being able to look at something like your cloud topology as a graph and be able to look for things like that. A lot of times those come in from more of the, I need to productionize my workload and be able to take the things someone has proven on their laptop and now actually scale it up to the size of data that we actually are dealing with.
So, in the fraud use case, clearly, if someone's a known fraudster, their associates, their connections are probably suspect. That's a rather obvious use case for it. Is there more to it? How does a graph help someone detect fraud?
Fraud in a lot of ways, what you're really looking for is it's an anomaly detection problem. So being able to look at what is a common pattern within of usage within your application, and then being able to find the things that are outliers and using those as the starting point for an investigation, because it usually still requires some level of, graphs aren't, they're not magic. They're not going to just tell you the answer. What they're going to do is help point you towards the most likely places to start. You may, really common pattern I see is to be able to run something like, okay, I have all of this transactional data, and I want, it contains things maybe like credit cards, payment amounts, addresses, emails, those sorts of kind of attributes that you would think most e-commerce sites, something like that might have. I might take that data, build my graph out of it, how these different things are connected, and then run something like a community detection algorithm on it. And then look at the distribution of those communities. Do I have a bunch of small disconnected communities, or do I have a few large communities? And then from there, I start to look at what is it normal there, because that's probably a good place to start my investigations. If all of a sudden all of the communities or groups of people that are highly tightly connected in my graph have an average of maybe 5 different nodes in it, and this one has 300 nodes, that might be of something of concern that I want to start looking at. I might want to start looking there to see what's going on, because this seems like it might be collusion. Or it could be the flip. You might expect a lot of people to be interacting, and you have things that are not, that are off over here doing whatever they're doing, and without hopefully not to be noticed.
When I think of use cases for relational databases, it's sort of low level in my mind. Like if I'm going to do machine learning, I might do some aggregations in the database, but ultimately I'm pulling out my training data and I'm doing my ML outside the database. Even though I know some databases, I guess, have some interesting built in stuff, I think that's a common pattern. Do people using graph databases have the same approach, or are there things like community detection that's baked in as a service?
I mean, I would say the answer there is both. There are some aspects of graphs, specifically if you want to look at ML with like graph neural networks, that can provide some unique aspects to a machine learning type algorithm to be able to do that. But I also see people using graphs and graph databases as sort of a, for lack of a better term, like a graph feature store, where you might use some of those graph features, a community, an influence value, as an input into into the feature vector that you're giving to a traditional XGBoost machine learning model, something like that. So I think it's a little bit from both. I mean, a lot of the patterns that I've seen in relational databases are very similar to the usage patterns I've seen in graph databases. Just, or I should say, maybe flip that statement. A lot of the graph database usage patterns are similar to the relational database usage patterns, just with a different technology kind of powering it.
And in your book, you feature the Glutton app as a good walkthrough and example. Could you share some details for listeners?
Yeah, so Glutton App was a fictional application that me and my co-author came up with to basically demonstrate some of the common use cases and patterns that you get with that are very commonly used with graph databases. It has a social networking aspect to it of being able to say, how are these two people related? So you can build a kind of a friend network for restaurant recommendation reviews. And then I sort of like personalized recommendation sort of functionality around it to be able to say, not only which of these restaurants is the most highly rated in the area in which I'm talking, but also which of my friends have rated this restaurant kind of the most, the most highly, to sort of kind of give that personalized, a more personalized response back to you, the end user.
And could you share some details on how that could work as a template for someone wanting to follow a similar path?
So yeah, the kind of idea of the book and the idea we kind of did as we did worked through this different pieces was really talk about, okay, here are these different patterns that we've seen very commonly used out in the applications, that we've worked on in the past, and being able to take those and simplify them down into kind of an end-to-end sort of example that is pretty relatable to people. People have, I would guess at this point most people have probably used restaurant recommendation apps. So being able to take that sort of common patterns and apply them to this specific thing, but at the same point talking about them as common patterns and breaking down the different parts and pieces that are required, to be able to take data, model those pieces out, start writing queries around it, and then start to look at how you would optimize that, which is a really kind of your general pattern applied to a specific problem.
So I find once I've built something, I then know how I should have built the thing. Having been there and done that, are there any sort of good advice for people starting out that maybe some pitfalls to avoid, things like that you could share?
Yeah, oh, absolutely. There's a lot of pitfalls with that I've run across in my years of working with not just myself, but also working with customers. But I think really the kind of the first key one I think about is really understand what problem you're trying to solve. Don't try to say I'm going to throw this data into a graph and I'm just going to get information out. That they're like every other sort of NoSQL purpose built type of database where you really need to, it's an optimized view on top of a set of data. So make sure you understand and optimize the data that, or optimize the graph that you build to solve the type of problem that you're actually trying to solve. If you're trying to solve a social networking problem, don't just throw all of the data in there. Just throw the data in there that you need in order to answer the question. A common pitfall that I see is people that have like clickstream or IoT type of data. They want to throw it into a graph, and it's not adding value to the types of questions you want to be able to answer. So make sure you kind of put the data that you want into the graph that answers the questions that you want to get back out.
I guess this is along similar lines then. How do I know if I even have a graph problem?
There's a variety of ways you can kind of think about this, but the way I kind of like to think about it is this a problem that requires you to look at how things are connected as much or more than what the things are themselves? So in just jumping back to kind of the social networking we talked about earlier, it doesn't really matter who the people are that connect the two of us. What matters is that they're connected and that you can draw this, this line between A and B in graph, it's kind of called a path, between A and B in order to get that answer. You don't necessarily care what all the individual pieces are in the middle. And the other thing is, a lot of times what we end up seeing people come to us when they have graph problems is they've tried this in other technologies and it's too difficult. Like you start to try and write this sort of thing in a relational database and all of a sudden you're like 5 pages into a SQL query and still not able to be able to, you're still not able to really get the answer you want out of it. So really kind of having that that moment of taking a step back and really say, okay, what is now that I to your point earlier, I've written it wrong. Now, what do I need to do to build it correctly? Being able to take that step back, think about the type of problem. Is this a type of problem that deals with connected data and connections between things?
So let's maybe take the case of the famous all pairs shortest path that most computer scientists should know. Anyone who took sort of a network science class should presumably know. And also recall that there are multiple algorithms that maybe work better or worse in different situations. Does my graph database solve that for me and pick the right one, or do I have some intellectual overhead in figuring out how to get an answer for all pairs shortest path?
I mean, the answer there is it depends a little bit on which database you use. So some of them implement multiple different algorithms. Some of them implement only one of the different algorithms. But when it really comes down to it, I would say a lot of times the actual implementation at the graph database level is already significantly more optimized than anything you're probably ever going to write yourself. So in some ways, you do have to kind of trust the experts on some of these things to be able to do it. It's useful to understand it, but it's sort of like a bubble sort. You probably shouldn't. Well, no, not you. Probably you should never write a bubble sort. Well, nobody uses bubble sorts, but you get what I mean. Like you shouldn't write this yourself, sort of thing. There's libraries out there that people have gone and built these sorts of things to be able to actually use that. Every once in a while, there are some use cases where you need to understand the which of the algorithms to choose. But in most cases, I found for most use cases for most people, the implementation that any library or database offers is probably going to be sufficient.
So let's say I invented my own social network and I wanted to add that feature where n degree friends. I guess there's two ways I could do it. I could do all pairs on some batch process and store, person A, person B in the distance, or I could do some sort of real time lookup as the page gets hit. What are the pros and cons of those approaches?
I mean, that's a similar problem we see all the time, and it really comes down to a few things. One, how often is your data changing? If your data isn't changing very often, then being able to calculate all of these things ahead of time and store them into a table gives you a lot of advantages as far as it gives you a constant time lookup. If you store this data into a Cassandra table or you store it into a DynamoDB table or in a relational database table, it's in one index lookup to find out this sort of information. The downside of that is one, you end up storing a lot of duplicated information. I mean, it's kind of a general NoSQL thing anyways, but you're going to store, your name is going to be associated with every single other person in the graph. So this can kind of lead to a combinatorial explosion. The other part of that is if your data is updating and changing, it gets very difficult to do what's kind of called truth maintenance, or what actually is the shortest path, because you can't run this algorithm every single time you actually want to do that. On the other hand, if you have a data that is updating frequently, something like that, you may want to do a more, you may want to calculate this at read time, where you're basically every time you're coming in, you might have a little bit of a slower query. You might not be able to do quite as much throughput, but that data is going to be very fresh. So it's really kind of a read versus write optimization. And which one's right is kind of depends on what the use case you actually want to be able to do, or you need to be able to support there.
And in terms of scalability, obviously there's managed services if I hopefully want to make that somebody else's problem. But even then, I know some graph, just the nature of graphs, some of the problems are NP complete. Those aren't going to scale very well. What does a typical scalability, I guess, picture look like for a growing organization?
I mean, I think there's a few different parts there. There's the data scalability of just being able to actually store more and more data. A million nodes, 10 million nodes, 100 million nodes, all kind of bring their own different challenges. But the other one that I probably run into more often than the data scalability problem is the query scalability problem. When you're writing into a graph, you're writing into this network. And when you query a graph, or called, traversing a graph, moving from point A to point B in that graph, you have to look at all of those different pieces in order to be all the different pieces that are connected in order to be able to find the answer. So if you have, a branching factor, or the number of connections that you kind of go out at each step is like 10, it means you mean every single hop you're going up by an order of 10. So it goes from 1 to 10 to 100 to 1,000. This starts to touch a lot of data very, very quickly. And that's usually where I see more challenges around the scalability is how much of the data you're touching in order to answer the question. Because the latency of any graph query really comes down to how much data you have to touch to be able to be able to answer it. So there's a few other things, but as a general rule, if I have to hit 10 times as much data, it's going to take 10 times as long. So that's usually where the more problem comes in. And it leads to this sort of thing in a graph that's known as like a super node, which is a node that has a disproportionate number of edges or number of connections to compared to others. So, the example I always kind of like to use is like, you look at Twitter. If you looked at my handle in Twitter, I don't know how many people I have, that are follow me, but it's going to be a relatively small number if you compare it to like Taylor Swift. She's going to have many orders of magnitude more people. So if I'm running the same query that says like find me all of my friends, okay, I'm going to go out, a few hundred nodes or something like a few hundred edges to answer that question. She's going to go out a few 100 million. So even though it's the exact same query, the starting location is going to impact the performance of that query quite drastically. The other part we see with that is the number of times I've had people be able to say like, but I'm only returning one value. Why is it so slow? Well, because you had to touch hundreds of millions of things in order to return one value. Those are the sorts of scalability challenges you get. The commonplace that shows up is when you want to return results ordered.
And as people are expressing, whether they're analysts or engineers, getting those queries written up, I know there's a variety of languages, but there's also a movement towards, I guess, GQL as sort of a standard. Do you have a perspective on the state of graph query languages?
Just kind of from a standards perspective, there's two basic data models. There's RDF, which has a W3C standard query language called Sparkle. And then there's the property graph data model, which is probably the one that I see more people using. That's the one we used in our book. And there's a couple of different standardized or open specification languages out there. There's Tinkerpop's Gremlin. There's OpenCipher. There's proprietary ones that Neo4j's Cipher, things like that. And then there is this movement towards GQL. It was only ratified, I want to say last year. It's relatively new. It's going to be very interesting to see how different vendors, start to move towards implementing GQL inside of their databases. I'd say, at least on the property graph side, all of them kind of have their pros and their cons. Gremlin, which is the version we use in our book, is a very powerful language, but that power comes with complexity, especially for new users of that language. I kind of often think of it as the stored procedure language for graphs, because you're really controlling how you move from A to B to C at a very low level. Whereas you have something like a Cipher, OpenCipher, and GQL is more of a SQL style declarative language where you kind of say, give me this pattern, give me something that looks like this pattern, and the engine itself handles all the optimization, which is easier to write, but harder to optimize if the engine isn't optimizing, because you don't get to control it. I mean, as things start to move to GQL, I hope they start to kind of give a little bit more of the control to the users in some scenarios, because as I kind of mentioned, some of the challenges with scalability, those show up in the query languages themselves too.
And broadly speaking, where are we on the adoption curve of all of the organizations that should be using a graph database? How many are?
I mean, I would say we're still early on the adoption curve for a lot of those things. So I think that there's two parts to that. There's the number of people that would use it, or number of organizations that are using a graph database versus the number of organizations that have data that they could get insights from that graphs can provide for them. And I think this is also not just on the graph database side, but also on those graph frameworks, those graph engines, and the types of unique insight you can get from a graph. I would say we're relatively early in most organizations who are being able to do that.
Well, the book is still pretty new, but it didn't come out this morning. What's changed in the time since you published it, if anything?
I mean, I think actually some of the pieces you've hit on there have changed quite a lot. GQL is now come out as a kind of an actual standard out there. Just still waiting on people to implement this. It's an ISO standard. It's going to take a little while, but that's kind of very new. I think also just the query languages themselves have really evolved since the book was published. There's a lot of, Gremlin specifically, there's been a lot of work around adding new features to Gremlin to make it more powerful for things like manipulating strings, manipulating dates, those sorts of things that weren't in it when the book was written, but are there now. I also just think in a lot of ways the use cases around graphs have changed somewhat. The rise of generative AI type use cases and being able to use, graph rag and things like that didn't exist when I wrote the book, 4 years ago. Well, I started writing the book 4 years ago. Under the covers, the problems are still the same. They're just different, different views on those same problems.
And could you give a just real quick lay definition of graph rag for listeners who aren't familiar with that yet?
I would say there's two definitions. I think there's the definition of using a graph. I don't like using the word knowledge graph but using a graph in conjunction with a RAG or retrieval augmented generation application to be able to provide kind of more complete and explainable answers is kind of one definition that I think, most people that are more familiar with RAG applications may think of. But I also see graph RAG used as kind of a catch-all term for using graphs with LLMs and generative AI as a whole. So it's sort of, I've heard, people come and say, I want to do query generation in my graph RAG application. But like, that's not really a RAG. There's no RAG part of this, but, it's just kind of become that catch-all term for graphs plus generative AI as well. So.
And if you were to really put your evangelist hat on, what's the best argument for an ambitious engineer trying to convince his organization it's time to do some R&D on graphs?
I mean, I think the best argument I have is to be able to show the data. It's always about showing the data. Find a use case that actually benefits from being able to use a graph and show that you can get significant performance improvements using that. Most enterprises have a lot of data sitting around, and being able to unlock, being able to use graphs to help unlock insight to some of that data that's sitting in S3 buckets or Snowflake or really, data warehouses, and being able to leverage it in those sort of scenarios is an area where I really see a lot of potential. I was working at a company once where we were working with family trees, and we were able to show that, not only were we able to scale better, but we were able to take the latency of a query down from about 5 seconds to about 500 milliseconds by using a graph database. You start to show, and if you start to take this in and you start to show the data of a 10x improvement, people will start to listen and start to see, okay, maybe there is something to this.
And what's next for you?
I'm very interested in where graphs are kind of going and what you can do, being able to unlock the different types of use cases that you're actually able to do with it. So it's very, I find it very interesting to be able to work with customers, see the very varying types of use cases that come out with this. So I'm very interested to kind of keep working with that and see where we can start to take this sort of technology to improve developers' productivity.
And is there anywhere listeners can follow you online?
Probably the best place to follow me online is to just look at my LinkedIn profile, which that's where I'm kind of posting most of the stuff I'm working on and things like that.
Very cool. We'll have links to all the above in the show notes, along with the book and your homepage. Dave, thanks so much for taking the time to come on the show and share your expertise.
Thank you for having me.